Okay, so in this section we're going to cover how to install the analog input card on your PLC. Most of you should have just blank gray covers on your 3 slots. Some of you may have existing expansion cards. I know at least one of you already has an IF2 on here, which is the analog card we're going to be using. And some of you have generic expansion input and output, just digital cards. So that we're all consistent on what is in what position, I'd like us all to have our IF2 card in this slot right here. So if you currently have anything other than that, one of the digital I/O modules, for example, go ahead and move it down to the end one so that your analog card is in this first spot. So for everybody else, if you have a blank cover, what you're going to do is just kind of squeeze this and rock it, and you can see it comes off. Please save this and return it with the trainer so that we can reinstall it if we remove the analog modules in the future. So then you're going to take your box of the new card, take scissors or whatnot, and cut the tape on the top. Go ahead and open it up. And inside you'll find that the module is inside a static proof bag, and you'll find these 2 screws inside. So we're going to go ahead and open the module. And then verify that it's what we expect, a 2080 IF2. And then if you look on the back of it, you can see there's one connector, and try not to touch the circuit board anywhere, as static from your hands can kill the circuits on the board. So we're going to install this by putting it straight down, and it snaps in place. But then also we're going to use our 2 screws that came with the module and a Phillips screwdriver. And just tighten them down firmly, but not so hard that you're risking cracking the plastic. Okay, and now our IF2 module is installed. So our next step is going to be configuring Connected Components Workbench to show that we have that new analog module installed. So we're going to do it 2 different ways. First, we're just going to start as if we had a new project. And you'll go through and select your controller just like we always have once it gets going here. So we're using a Micro850 24QBB. Okay, add that to the project, and then it's going to come up with the default page showing all the information about the controller. So if you look down here in the project or the controller tree, you'll see that down under there's the general controller, motion, and then plug-in modules, and you'll see there's 3 slots. So right now slot 1 it shows is empty, and we're going to add an analog card, and the card you have is a 2080 IF2, so we'll select that. Then it gives you information to set up each of the 2 channels, so that's what that 2 there means. There's 2 analog inputs, so I for input, F is the analog, and 2 means there's 2 channels. And we're going to set them both up to be voltage. So we're using voltage as the source, and we're 60 Hertz is where we are. And voltage and 60 Hertz is fine there too. Okay, so now we have configured that so you could save this project. And now if we go, let me save that, and then go look at the global variables, we should have different inputs than we did before. Okay, so here's our normal digital outputs, 0 through 9, so 10 of them. Digital inputs, 0 through 13 for 14 of them. And if we scroll down to the bottom now, you'll see that there is I/O, so it's an I/O card. Then P1, so it's in our first spot. and then it's an analog input, and it has two channels, 0 and 0, 1. So that's a new input that we can use. So that's one way to configure it. And I'm going to go ahead and start again. And this time we're going to, let's discover instead of creating a program from scratch and see if it can recognize that module being installed. So I am going to unplug and plug my USB to refresh that since it's not showing up. Okay, now it shows up on USB. Say OK. And let's see if it can figure out on its own that it has that module installed. And it can. You can see that the image updated. It shows the module. And down here, you can see IF2, but the configuration is not set since we didn't save that and download that in our previous program. So let's go ahead and set that to voltage. And then let's upload from the controller. So I'll grab a program out of it. Actually, I'm going to cancel that. I forgot to change this to 60. Okay, now we'll upload. And one thing, I think it's probably, I might not be able to see it now, but down in the output, when it was first connecting and discovering to the module, it did give me a little notice in there too, letting me know that it saw a new module that it hadn't seen before. And I can't see that now since I moved on from there. But okay, so now I am connected to the controller. I could see the program in it. This program is unrelated to this lesson. It's stuff I'm working on with the motion controller. But I'm online with it. And if I so when I uploaded it, overwrote the new configuration. So let's go back and redo that. So disconnect that, and we'll just set it up. Edit IF2, voltage 60, and now we'll download that. So this way I have got the program out of the PLC, so I'm not overwriting my program, but I've updated the controller information so now it knows it has that analog card. Okay, so now I am back. I'm online with the controller. I could look at my program in there, and if I go look at the global variables, I should show an analog. I show my two analogs, and you can see right now it's bumping around 15 or 16, and we'll talk more about what the units are of those once we actually connect the input, the physical input itself, up to a device. So that's two different ways to configure it. One is by entering the information itself, and the other is by discovering it. Okay. Okay, so now it's time to connect the IF2 module that we've installed on the PLC to our analog potentiometer. And before we actually do the hardware connection between that input device, the potentiometer, and our measuring or input card on the PLC, the IF2, I wanted to talk some more about analog inputs in general. So the analog input that we're going to use is a potentiometer. If you remember a potentiometer, the schematic symbol for it is basically a resistor, but then with a third tap on it that's adjustable. And you can think about this as this is a contact that moves up and down along the resistor as you rotate it. So the potentiometers we're using are a 5K ohm potentiometer. So if we numbered these 1, 2, and 3, the resistance between 1 and 3 is always 5,000 ohms. The resistance between 1 and 2 will vary between 0 and 5,000 ohms depending on the position of the knob, and same with the resistance between 2 and 3 will also vary from 5,000 to 0, and whatever R1 at the resistance between R1 and R2 plus R2 to R3, that will equal 5,000 ohms. So basically at any time, if you put your meter across 1 and 3, you'll get 5,000 ohms. If you put it across 1 and 2, let's say it was at a position of the knob that there was 1,000 ohms between 1 and 2, then you'd know that there's 4,000 ohms between 2 and 3. So that's kind of just a refresher of what the potentiometer is. We are using these both. We're going to use the potentiometer, and we're going to set up our card to be looking at an analog voltage. So far we've been dealing with digital inputs and outputs. So digital inputs on our PLC are 24 volt DC. So their input can be either off or on. And basically that value is either 0 volts or 24 volts is the nominal, we would call that. We would say an off is 0 volts and an on is 24 volts. We can look up the actual specifications for that. Let's go ahead and do that real quick. Okay, so I'm going to go to my references, open up the user manual for our controller. Remember, we're using a Micro850. And then I'm going to look at the specifications for it. And specifications for a Micro850. Okay, and looking through the various, I'm going to scroll down here. These are just kind of general across all of the models. But we're looking for input ratings. Okay, this is looking like we're getting there. So you can see here we're 2080 LC50 24 QBB, so that's ours. And then you can see in the chart they've broken down the inputs into two groups. The first 8 that are high speed, and then the second 6 that are just standard DC inputs. And what is of interest to us right now as we're talking about inputs, you can see that down here in on state voltage range, what it considers an on, in other words, is between 16 to 26.4 volts. So that's where I said that basically 0 is off and 24 is on. Really what this means is that anything above 16.8 volts is considered an on. And if we look down a little further here, we'll see that off state voltage max is 5 volts. So again, anything below 5 volts is considered an off. So those are the voltage levels for our digital inputs. I just want to point at, just taking this opportunity to talk about that while we talk about it being 24 volt DC inputs, there really is a range in there of what voltages it will consider an on. So if you fed 18 volts into that input, it would consider that a on. If you fed in 10 volts, it wouldn't. That would cause a problem for the hardware because it would be more than its off state and less than its on state. So we want to feed it less than 5 volts for our off and more than 16.8 volts for our on. So I hope that makes sense about voltage levels in our digital inputs. But now we're talking about analog inputs. And that's going to be a little different. Let's look up the specs for our 2080 IF2. So I think I might have here, this is let me make sure which reference I have. I think this is the user manual for our plug-in modules. Yep. So we're going to go down and look at our 2080 IF2 2-channel. So here, we're starting to find information. It says it's a 2-channel, non-isolated unipolar voltage current analog input. So let's break down what that means a little bit. 2 channels, pretty obvious. There's 2 analog inputs on this card. Non-isolated means that there's no electrical isolation inside the module. So if we get a high spike or bad voltage on our input, it could get into the card and damage the unit itself. So a lot of the time when we have analog signals, we want to isolate them. But these are fairly inexpensive little modules, so they are non-isolated. Unipolar means that the signal is referenced to one. It's only a positive signal. So if you're looking at voltage, 0 volts, we're going to only have analog voltage above 0 volts. So we can have a value that ranges, but it can't go negative. This part would not work with this card. There are cards that go negative as well. So we'll get into that a little bit more when we get down further into the specs. Second, the next piece of information is its voltage and current, or voltage or current. So we can choose whether we're looking at an analog voltage or an analog current. And again, we'll talk about that more as well. So let's keep scrolling down, see if we get some more information about these things. Okay, so here we are on our analog plugins 2080 IF2. So here's the next piece of information, unipolar, we knew that, but here is the range, 0 to 10 volts. So this can go, our maximum voltage we would want to put in is 10 volts, and the minimum it will read is 0 volts. So that's because it's unipolar. There are other expansion cards that go onto the end of this module rather than snapping onto the top of it. They're a higher resolution, and they can be bipolar or allow for negative 10 volts. So instead of being 0 to 10 volt, they could be negative 10 to 10 volts. So a wider range, and there's some signal integrity benefits to having that negative and positive side of the scale as well. But for us, we're using a unipolar 0 to 10 volts, or you'll notice 0 to 20 milliamps. So we could set up our card to be looking at either 0 to 10 volts or 0 to 20 milliamps. And lastly, it says offers 12-bit resolution. And we'll talk more about what that means later on in the module as well. Okay, so now we know that for this card, what we want for our analog input is somewhere between 0 and 10 volts, and it will measure what value we have between those. Okay. So the last piece of information I want to get out of this user manual before we move on is to take a look at the specifications for our IF2 manual, or IF2 module. So if I come down to the specification section, look at analog plug-in modules, you can see here kind of a summary of the things we just went over. So our card, IF2, has 2 inputs, single-ended. That's another way of saying unipolar. Analog normal operating voltage ranges is 0 to 10 volts. We'd figured that out. Or 0 to 20 milliamps. Here we have information about the resolution. So it says 12-bit resolution. So if you think back to bits, that's a 1 or a 0 in digital storage. And so for each bit, we double the number of values we can represent. If you remember back to, if we have a 1-bit number, we can only represent 0 or 1. If we have a 2-bit number, then we can do 0 through 3, which would be 4. So, 2-bit, 1 bit equals 2 values. 2-bit equals 4 values. 3 equals 8, etc. And so if you look at those, you'll see that a way of figuring out the actual numbers you can represent in a binary number is 2 to the n power, with n being number of bits. So for example, for 2 to the 1, that's 2 to the 1 is just 2, right? Just like we said. 2 to the 2, that's 4. 2 to the 3, 2 times 2 times 2, that's 8. So if we're saying 12-bit resolution, that would be 2 to the 12th. In that case, 2 to the 12. So that's 4096. So it's saying that is the resolution. And I'm pointing out, actually doing the math here, because if you look down at just one more line here, it says the data range is 0 to 65,535, which that number, if you happen to recognize that's 2 to the 16th. So if we say 2 to the 16th, we get 65,536 values. So 65,535 would be the highest number it could reach. So that's quite a difference, right? It's saying the data range would be 0 to 65,536, but the resolution is only 4,096. So you'll see that when we actually connect up our sensor and wire it, the numbers will range between 0 and 65,536. But in reality, they're only guaranteeing the resolution or the accuracy to be 4,096. So that doesn't mean just 0 to 4,096 out of that 65,000 is accurate, but it does mean that within that 65,536, it's only accurate to 4,096 of 1. I'll explain that more as we look at the number later on. One thing I skipped over there too was about the frequency here. You can see how often it samples. At 50 hertz, so 50 times a second, 60 times a second, 250 or 500 times a second. And other things, input impedance, that's important. You can see that when it's measuring voltage, it has a very high impedance, 220 k ohms, versus if it's measuring current, it's 250 ohms, because it doesn't want to be a huge block to the current. You only have typically 24 volts driving the source, and you want 4 to 20 milliamps, sorry there. So that's why it's a lower impedance when you're measuring current. Some more information on accuracy. And I think that's probably enough information about the specifications for this module. Key things I wanted to point out is it can measure either 0 to 10 volts or 0 to 20 milliamps. So let's talk a little bit more about voltage versus current on analog inputs. Most analog inputs, you have the choice whether you're going to use a voltage sensor or a current sensor. The current sensor is probably going to be more common in industry that you'll find those, because it's more robust against noise or wiring issues in the circuit. And let's think about why that is. If you have a 4 to 20 milliamp circuit, that's the most common. Couple things, let's just start out thinking, why 4 to 20 milliamps? Why not maybe 0 to 20 milliamps? And the one answer there is that they're often loop powered devices, so there's some current flowing through the circuit at all times to power the individual devices. So the sensor wouldn't need its own independent power source, for one thing. The other is that if you have your minimum value as 4 milliamps, if the circuit breaks, you can see that, right? 0 milliamps is an error condition then, not just a minimum value. Back to like similar ideas when you have a normally closed circuit for your safety devices, so that if something gets knocked loose or torn, you notice that as a fault condition before something bad actually happens. So 4 to 20 milliamps is most common. Like we're looking at the specifications, our module can actually measure 0 to 20 milliamps. So there are sensors that use 0 to 20, and that's fine. We'll just scale our output depending on what we're looking for, whether our sensor is a 4 to 20 sensor or a 0 to 20 milliamp sensor. So again, nice thing about current loops are they're relatively less sensitive to issues with connections in the control loop, the sensor loop, because any resistance that gets added into the loop, if it's current, what's going on in a current loop is your sensor. Let's say we have a positive and a negative source. Let's say we have a DC 24 volt source, and then let's say we have a level transmitter. I'll call that, and it is a 4 to 20 milliamp device, and it's going to have two terminals, and And then we have our PLC input that's set up for current. So I'm going to call its input C1, and then its other terminal would be a common. This would be, let's call it PLC A1. That's an analog input. So if we're wiring this input loop, we'd take our positive supply, go to the level transducer, out the level transducer to the current input of the PLC. PLC does its measuring internally, and then the loop is completed by returning to the source. So what's happening here is most of these sensors would be a loop powered device. So this transmitter, it's getting its power from the DC supply, and with that voltage that's applied to it, it then measures its value. So if this is a level transmitter, it's measuring either by pressure or some other sensing technology. It's reviewing what is the level of the fluid I'm looking at, and then it varies its own internal resistance to create 4 to 20 milliamps of current on this loop. So let's say when the tank is empty, it's going to adjust its resistance so that 4 milliamps flows through this circuit. If on the other hand it's all the way full, then it's going to adjust its own internal resistance so that 20 milliamps is flowing in the loop. And so what's great about that is, say this connection here between this wire between the level transmitter and the PLC, say it's 1,000 feet long or something. Even though a wire has very little resistance, it does have resistance. So if this was a voltage signal over that 1,000-foot line, you would drop some of your voltage that would look like it was being changed by the transmitter. It's actually just being lost in resistance in the wire. Whereas if it's current, the level transducer is managing the current at this point here, but as we know, in a circuit, the current is the same everywhere in a series circuit. So even though the level transducer might be 1,000 feet away from the PLC, as long as it's measuring or controlling that there's 20 milliamps through the circuit at the transmitter, you're guaranteed that you're going to have 20 milliamps through the PLC as well. That's not the case if instead of being a current loop, we did a voltage source. So let's look at, so if this was a current loop, analog input, let's look at a voltage analog input. Okay, so again, we'll have our positive supply, and we can say it's a level transducer again, but now instead it outputs a voltage. This is going to be a little different. So now we have our level transmitter, and it's going to have a power supply. You're going to bring positive and negative to the transmitter, and we'll have our PLC over here again. Now it's V1 in common, PLC analog 2, let's say, and now it's going to put out a voltage, and this would just reference typically the same ground or not ground, the same negative supply reference. So it could either be common coming back to here, or maybe it's coming out of the transmitter, but they're referencing the same lower voltage level from both the transmitter and the PLC. So now you can see that if there's resistance over this long wire here, if this is putting out 0 to 10 volts like that, if there's enough resistance in this wire, even though the level transmitter is putting out 10 volts, you might be getting something like 9.75 volts at the PLC input. Also, this is more sensitive to induced spikes on the line than the current as well. So you can get a noisier signal on a voltage signal than in an analog signal. So that's one of the reasons that analog is more common, kind of more robust, a little simpler to just add devices into the circuit. You can have multiple sensors reading the 4 to 20 milliamp. So you could have the PLC monitoring it. You could also have a panel meter monitoring the same output of the level transducer by just putting it in line somewhere else. So you could have panel meter, something like that, in the same loop, because you have lots of devices that are reading the 4 to 20 milliamps. You can only have one that's controlling it. Okay, that's kind of an overview of analog versus voltage. We are using a voltage source just for ease and affordability. We can use this potentiometer as our voltage source very cheaply compared to a current type transducer. Has a lot more circuitry in it. You could use a potentiometer as well, if actually depending on if you wanted to wire it up yourself. But for what we're doing, we're using a potentiometer as a voltage source. The last thing we want to talk about is how do we, I talked about spikes on the signal, especially on the voltage side. How can we try to minimize interference on our analog signals? And one of the most common ways we do that is we put a shield around the signal wires. So what that means is you have a braid or a foil, some metal conductor that's wrapped around the signal wires. And what it does is it diverts any spike or pulse from nearby electronics. It tries to shunt that to ground before it can affect the current or voltage on the signal wires themselves. So it's important to note that shield gets tied to ground, not to either of the lines typically, not to the negative voltage reference or zero voltage reference or the signal itself. Same with up here in current. The shield, we show a shield and we tie it to ground. Okay, and as we wire it up, I'll show you an actual example of what that looks like physically. Okay, I think we're pretty close to being ready to wire the input on our analog card. Last thing we want to do is look at the installation manual for the card. We've reviewed the user manual quite a bit to figure out the specifications, but now we're going to take a look at the the installation manual. Okay, so this is the user manual we were looking at previously. Here I have the installation manual for our non-isolated unipolar analog input. So it can brief document, just 8 pages, but what's important in it is it will have the actual pinouts for where we're going to connect our wires. So you can see here this covers the IF2, IF4. Let's scroll down, take a look at these. There's the physical description. Reminder to be careful when you're stripping the wires that you don't let any fragments get inside the module itself. They say you're allowed to put up to 2 conductors under any terminal. That's great. Cable length should be less than 10 meters. So this is one of the limitations to unipolar 0 to 10 volts, relatively short cable lengths. If we wanted to have a longer cable length than that, we would likely go to a current loop instead of voltage, or at least go to a negative 10 to 10 volt signal. Okay, so here's our wiring pinout. The terminal block, you can see it's got 2 rows of 6 terminals, and we're looking at the IF2. So if you look at the pins for IF2, you'll notice that pins A1 through A6 basically aren't used. So we're not going to use anything on this lower row. Everything we're going to connect to is on row B. So looking at row B, you can see that B1 is voltage input 0, B2 is current input 0, and then B3 is the common for those two. And then 4, 5, and 6 are the second set of those. So we would pick, are we using B1 for voltage? In which case we will hook up to pin B1, or are we using channel 1 for current? We'd hook to pin B2. And for our purposes, we're going to use the second channel, and we're going to use voltage. So our connections will be to pin B4. That's where we'll bring the actual voltage signal. And then B6 will be the reference, our 0 volt reference that we're comparing the signal to. So in this case, that would be our negative of the power supply. Okay, we've already installed the module. Here again, there's the specifications for it. 0 to 10 or 0 to 20 milliamps. It tells us about the power consumption. You'll notice this one is kind of a smaller set of specifications compared to the one we found in the user manual. It doesn't tell us anything about the data format. That 65,000 doesn't tell us about the accuracy or whatnot. This is just physical information or electrical information that's necessary for installing the unit. Okay, so we've covered the user manual, found out the specifications. We've gone through the installation manual for information about where we're going to land our wires. We talked about benefits of current or voltage. We touched on shielding the signal wires. I think that's good about the module. The last thing we're going to do before we actually wire up our module is I'm going to show you what is going on behind the panel on the potentiometer to look at how are we going from 24 volts, which is the DC supply we have on our trainer, down to the 10 volts range that is allowed for our card. So hopefully that makes sense. We've only got a 24 volt source. We don't have a 10 volt source on this board. So how do we get our potentiometer to adjust from 0 to 10 volts? So let's go talk about how we did that. Okay, so let's look at how we take the 24 volts that we have available to us on our trainer and we turn it to a 0 to 10 volt signal using our potentiometer. So we have on our trainer already, we have a 24 volt power supply, right? It takes 120 volt in AC, and it gives us out a positive and a negative 24 volt DC. And I shouldn't say that it's not a negative DC voltage, right? It gives us 24 volt DC. One is our 0 voltage reference. We'll call that negative because that's how they're usually marked, and then our positive 24 volts. It's 24 volts above that reference. Okay, and then our PLC over here, analog input, it's looking for a 0 to 10 volt DC. So we talked about what a potentiometer is. It's a variable resistor, and between 1 and 3 it's always got a fixed value. So if we hooked up terminal 3 to our negative supply and we hooked up terminal 1 to our positive supply, by rotating the potentiometer knob, terminal 2 would vary between 24 volts and 0 volts depending on where it is. Let's just draw that up. So if I came, I'm actually going to change this to make that a little more clear, make it easier to not overlap wires. So our positive coming to the top of the potentiometer and our negative coming to the bottom of the potentiometer. So in this configuration right now, let's say I turn the knob all the way to the right, and that would put our terminal 2 all the way up at the top. In that case, all of the resistance drop is below terminal 2 and 3. So in this case, when I have the resistor all the way up, or the potentiometer all the way that way, the voltage would be equal to 24 volts. Then if I turn the knob the other way and crank this down to where my third terminal is looking at this end of it, now my voltage would be 0 volts. So with just one potentiometer, I've got a 0 to 24 volt supply, which I could use that, it would up to 10 volts for basically the bottom, 40% or so would get a value. But once I went above 10, the PLC would just show it always as the maximum, above 10 volts. And it might even damage the input of the analog input card. If I put 24 volts on it, I'd have to look up the specifications to see. So what I want to do is get to where I have 0 to 10 volts by adjusting the potentiometer instead of 0 to 24. So what I did to do that is create a voltage divider. And if you think back to Mech 131, start on a new piece of paper. If I have two resistors in series, the total voltage drop across them would be equal to the total supply of the circuit. So I can tell you that my potentiometer is 5,000 ohms, is its value from one end to the other, 5,000 ohms. So if I want to adjust my total drop so that across that the potentiometer I get 10 volts drop, that means I need to drop 14 volts across the resistor on top here. So let's call this R1, and this is our potentiometer. So I need to figure out a value of R1 that will result in about 14 volts of voltage drop across it and leave me 10 volts across the bottom. So I know one of them. So if I want the total voltage drop across 5,000 ohms to be 10 volts, I need to figure out what's the value that'll get me about 10 volts left from 24 volts. So I'm going to pause for a minute and let you think about how you could use Ohm's law and your previous experience to figure out the value for R1. So do actually stop and think about, I encourage you to try to come up with your own value for R1 that would result in a voltage drop. Basically we would have 0 volts here, 10 volts here, and 24 volts here. How could you figure that out? Okay, so hopefully you came up with your own answer. I'll walk you through how I did it. So I knew that the potentiometer I had is 5,000 ohms nominally. Of course, they have a tolerance plus or minus 10%, 20%, something like that. But in theory, it's a 5,000 ohm potentiometer. And I know I want to drop 10 volts over that. So if I think of Ohm's law, E equals I times R. In this case, I know the voltage I want and I know the resistance. The unknown right now is the current through that circuit. So I will rearrange that to I equals E over R and plug in the values I have, which that's the voltage is 10 volts and the resistance is 5,000 ohms. So 10 divided by 5,000 is 1/500th or 2 milliamps. Let's see here. Hopefully you can see that. Another way to write that right would be 0.002 amps. Okay, so I know in a series circuit that the current going through that potentiometer when it's 10 volts is going to be the same current going through this resistor. And now I know that I want to drop 14 volts over that resistor. So I'm just going to rearrange Ohm's law again now to solve for the resistance. So if E equals I times R, then R, the resistance R1, is equal to the voltage across R1. So we'll call that VR1 divided by, or E, I'm sorry, I'm so used to using V, ER1 divided by the current through R1. So in that case, we want to drop 14 volts across it, right? That's the difference from 10 volts to 24 volts. So 14 volts divided by 2 milliamps, or 0.002 amps to keep my units easy. So 14 divided by 0.002, that results in 7,000 ohms. So I would want an R1 equal to 7,000 ohms. Now, unfortunately, resistors don't come in infinite values. You can't get a 7,001 ohm or a 7,002 ohm. I couldn't even get a 7,000 ohm resistor easily. The nearest one that I could get easily was a 7,500 ohm resistor. So I ended up using a 7.5 k ohm resistor. So let's figure out what that resulted in. So let's draw my actual circuit that I used. So this one's 5K and this one's 7.5K. So let's add that up. I get 12.5 k ohms is the total resistance in the circuit, and the total voltage across the circuit is 24 volts. So let's figure out the current through the circuit. In that case, I is equal to E over R again. So now I'm looking through the whole circuit. The voltage is 24 volts divided by total resistance of 12,500 ohms. So 24 divided by 12,500. So I get a current, you can see, a little less than what I'd ideally wanted. So I get 1.92 milliamps. So what that means is that my voltage drop across my potentiometer is going to be a little less than 10 volts total. And that makes sense because ideally what I thought I needed was 7,000 ohms, but I ended up using 7,500 ohms because it's what I could get. So let's figure out what our theoretical voltage range on our potentiometer will be. So we have 1.92 milliamps and it's the 5,000 ohm resistor. So voltage E equals I times R. So that's going to be 0.00192 amps. That's 1.92 milliamps times the resistance of 5,000 ohms. So times 5,000. So I get 9.6 volts. So in theory, I'm going to get a range from 0 to 9.6 volts from one end of the range of the potentiometer to the other. And that's fine. That's less than 10 volts. Let's say I had gone with, instead of going with a 7,500 ohm resistor, the next common one might have been a 6.7 k ohm. If I had done that, hopefully you can see that my range would have been a little more than 10 volts. So in this case, I settled for the 9.6 volts to make sure I stayed within the range of our PLC input module. Okay, so that's the calculations. I have a 5K potentiometer and a 7.5K resistor in series with it. And now I'll go show you what that actually looks like physically. Okay, so here we're looking at the I/O panel. I've removed the analog input, the potentiometer. So you can see it's right here. These are the three terminals. Two of them are shrink wrapped. One of them has a wire leading into this cap. And so you can see there's this cap on the back of the potentiometer. That's not part of the potentiometer itself. That's a separate little part. This is one of the prototype ones from when I was making it. And what's inside that cap is this resistor, a 7,500 ohm resistor like we talked about. So you can see there's a little pocket in the back of the cap that the resistor sets down in like that. Sorry. And then the whole thing just snaps onto the back of the potentiometer like that. So then that resistor, if you're looking at it, the lead, one of the leads from the resistor is wired down over and connected to one end of the potentiometer. Remember, between these two outer terminals of the potentiometer is the full 5,000 ohms. And then this middle one, the resistance changes based on how we rotate the knob of the potentiometer. So basically, if we're looking at our schematic from before, like this, it would look something like this. We have power coming in on this brown wire, which I've removed. It comes in to the 7,500 ohm resistor there, goes through the resistor, and then comes to one end of the potentiometer. So this point right here is the same as that point right there, where the potentiometer connects to the resistor. And then the next terminal here would be this middle terminal, or the white wire. And finally, the last outer terminal is the blue wire, would be the other end of the potentiometer heading back to ground. So let's do some resistance measurements across those to kind of verify what we did as far as design. So across the outermost terminals of the potentiometer, I should get somewhere around 5,000 ohms. Again, these are, I think, 20%, maybe 10% potentiometers, so they can vary within that range. I have removed one of the wires from the circuit. Remember, we always do that when we're measuring resistance to make sure that the rest of the circuit isn't influencing our resistance measurement. So if I measure across the potentiometer, I get 4.85 k ohms, so a little under the nominal 5k. If I then measure from the one side of the potentiometer to the other side of the resistor, I should get somewhere around the 7,500 ohms. Let's see what we get. About 7.45 k ohms. Okay, so the total value of each one is a little less than what we anticipated. Let's just kind of check about how the potentiometer works, the variable resistance part as well. So we said we have about 5,000 ohms. What do we have total? 4,850 ohms across the potentiometer. So measuring between the two outer terminals and the inner terminal, we should get values that add up to that. So between the lower terminal and the middle terminal, I get 2,629. So I should get about, if we were at 4.8, I should get about 2,200 something between the middle one and the top one. And I get 2,342, 2,629. So you can see they should be pretty close to adding up to each other. They'll always be a little bit more if you add the two partial resistances from one terminal to the middle and then from the middle to the other one. They'll always be just a little bit more because the wiper that is moving along the radial resistor adds a little bit of resistance itself. So there's always a little bit more if you add together the two than if you go straight across the outside. Okay, so last measurement we can make, I guess, would be all the way from the resistor to, sorry, it's beeping because it was getting ready to turn off. If I go all the way from the resistor to the other end of the potentiometer, and I get 12.29k, and we had said I should have around 12.5k. Okay, so that is what is going on in our potentiometer. That's how we're using the potentiometer plus another resistor as a voltage divider to get an adjustable 0 to 10 volts out of our fixed 24 volt supply. So I will put this back together and then we'll talk about how to connect the potentiometer to the analog input card. So I realized one other measurement we can make now before we connect up to the PLC, just to verify that our calculations all worked out, is let's measure the output of what the voltage is on the adjustable terminal of our potentiometer with our 24 volt supply as we rotate the potentiometer knob. So I'm going to measure voltage now instead of resistance. I'll put my black lead on the ground or the 0 voltage reference of our supply, and my red lead is on the output, which is the white wire of our potentiometer. So with the knob all the way to the left, I'm at 9.4 volts. As I rotate it, it's decreasing down to 0 volts when it's all the way at the right. So it looks like our voltage divider and potentiometer circuit are working fine. They're a range from 0 to 9.4 volts. Okay, let's look at how to connect that up to the PLC now. Okay, so now we're going to connect to our IF2 input card to the potentiometer. And the potentiometer is already landed on a terminal block down here. And so we'll use the signal coming from the terminal block on this white wire gray block. We'll also use the 0 voltage reference. So the analog signal will be between our 0 volt and then this block here. So we need to bring those up to the common. Terminal 6, B6 will be our 0 volt reference. And then if you look on your block, you can see there that input 1, the second input, if we're using a voltage, that's going to be on terminal 4. So we're going from terminal 4 to this gray block and from terminal 6 to a black block. And in this case, any of the black blocks or anywhere we have a black wire here that's referenced our 0 volts will work. So I'll probably I haven't decided yet which one I'll land it on, but just pointing out that electrically these are all the same potential. It should be 0 volts. And just to demonstrate that, let's grab our meter again. And on DC voltage, power supply is on. So let's check we got 24 volts on our supply. We do 23.99, and then if I check voltage between any of these, I should have essentially 0 volts between any two black wires. And that's what it's looking like. So that's just verifying that any of those could be used as our 0 reference. Okay. So now let's talk about the wire we're going to use. In your kit, you'll see that you have a piece of this black wire. It's got 2 twisted pairs in it and an overall shield. So reading the side of yours, you'll probably see mine says shielded there, and then I'm missing the rest since it's a relatively short length, but probably yours will say 2 twisted pairs and the wire gauge on it. So this is instrumentation cable. It's got, like it said, 2 twisted pairs, and we'll go ahead and save the pair that we're not using. So obviously we just need 2 wires for what we're doing right now, but don't cut off the other 2 that we're not using right now, because later on, if we have a time in this class, we'll add an analog output module as well. Because of the weather delay, I'm not sure we'll get to that this time, but just know that that's why we have 2 twisted pairs. So here I've already stripped one end, and you can see that there's a black and white twisted around and a black and white twisted around. And if you look closely, you'll see that they're numbered so that you can distinguish which one goes with which if they get separated. But the key thing that's different about this wire is you'll notice there's this 5th conductor in there, a bare conductor. And I've already torn the foil off, but we'll see in a minute that there's also a shield. And this type of instrumentation cable is called overall shield. So there's just one foil that wraps around both sets of twisted pairs. There's also another level of shielding that has both individual shields, so there's a foil wrapped around each twisted pair, and then an overall shield as well. That provides even more isolation. That provides isolation from each pair to itself, as well as from external signals coming in. So just a reminder again, the purpose of the shield is if you had this wire running near another wire that had high current or high voltage spikes on it, the current flowing in that other wire, if it's running alongside our wire, just like a transformer, it can induce voltage into our signal wire. And we want to avoid that, especially on analog signals where we are looking at very fine changes in the voltage. So the shield, the purpose of the shield is it is a ferrous, it's a metal guard around it that intercepts that magnetic field and shunts it safely to our ground. And again, I'll make the distinction that the shield gets tied to ground, not to our 0 voltage source. And here again, because we're on the trainer, things are a little different. We're working on a wood panel. We don't really have a good ground point. Typically, this would be a metal back panel, and we would have a single point on the panel where we brought all our earth grounds to, typically a stud on the corner of the panel. The only place that really has a ground on the panel right now is this as the ground terminal of the power supply, and it's getting its ground through the 3rd prong of the power supply back into the building wiring system. So we actually are not going to tie our shield wire to anything in this case, but just know that typically that's where you would be landing it, on a metal panel. In different cases, you would either tie the ground to the control panel, or you would tie it to ground out in the field environment where the actual sensor is, but you would not tie it at both ends. You don't tie the grounds together through the shield. So you pick one end or the other that you're going to tie the shield to ground on. Okay, so let's look at stripping a shielded, really any multi-conductor cable, but especially one that's shielded. There's a couple different ways you can do that. There's different types of strippers that are intended specifically for that task. I've shown you guys these before in Micro850. This is one type. If you can see, you press on it, there's a blade right there. And so I'll use this one first as an example. You put it in, and then the spring tension presses that knife blade into the jacket, and you gently spin it around a few times, and then bend it to break it and pull the jacket off. So that's one way. That's great. That's a nice little tool for doing this. And here you can see the overall shield. So you can see there's the wire that's in contact with the foil shield, but then this piece of foil is the actual shield itself. So you can see I'm peeling it off. And so it's the foil that's actually providing the shielding function throughout the wire. But then on the ends where you need to land that shield to ground, you're going to use this wire that's laying inside the shield, because you can't really terminate the foil. So right now, if I was going to land it, I could land my white and black wires on the PLC, and then again, if this was a real application, I would land this shield wire on a ground terminal. So that's one way to strip it. Another way, if you don't have this type of stripper, is to carefully do a similar function with a sharp knife. So I don't have a sharp knife here, this one's pretty dull, but I will show you the same idea still functions. And here you're just being more careful, so you're kind of scoring it, and you can see how I'm bending the wire at the same time to put stress on it. So you can see I'm starting to get through it, and you can see I just starting to get down to the shield. So then I would turn it a little and do the same thing again, and you just work your way around, gently cutting through it, hopefully with a sharper knife than I'm using here, and just do that all the way around until you've got all the way through, and just twisting it until you break the jacket. Okay, so there again, got the jacket loose. You can see the shield again, and peel the foil, and then you can terminate the shield wire. Okay, that's one method. The last one I'm going to show you is you can just use the same type of wire cutters as we've been using, and doing the same thing, just gently watching as you rotate it. You can see I'm just starting to break through. So the idea is you're never cutting fully through the plastic jacket or rubber jacket. You're scoring it to get to the point where you can then kind of bust it like that. Okay, so those are all valid ways of doing that, and then peeling off the foil shield. Okay, so I am going to cut off a clean end and do it for real now. And so let's plan out how we're going to land our wires. So I'm going to have a black wire landing on terminal 6, white wire landing on terminal 4. And then on the other end, I need to get a white wire down here to this gray terminal, and a black wire could land on either this one, or I could even run it back to this one. Those would all be adequate. So I'm going to turn off power and make sure I don't accidentally short anything out here. And I just want to kind of point out, this is not the typical application for shielded cable inside a panel. I'm running just a few inches here from a terminal block to my analog input card. So in reality, what would normally be happening is you'd run wire from here to a terminal block, and then run shielded cable from the terminal block out of your control panel out into the industrial environment is where you would be using the shielded cable. So this is just for practice, so that you have the experience of stripping a shielded cable and terminating it. And I'm just wanting to acknowledge now that this is not a typical place that you would be using this. And it's kind of an awkward place to be using it, because you can see the jacketed wire is quite a bit stiffer than just individual conductors. If I just stripped all the jacket off this and used the twisted pair, that'd be a lot easier to route my wires. But I want you to get the practice of carefully removing the jacket without nicking the conductors, and just get experience working with foil. So I'm going to go ahead and do that. So I'm going to strip enough wire so that unjacketed wire can come from the terminals and then down into the wire duct, and then strip another length on the opposite end again so that I can get it out to here. So you can see I want to strip at least, that much there, so I'm going to probably strip mine right about here. And sometimes if you're stripping a longer length of jacketed cable like I am here, sometimes you have to do it in 2 different steps, as it might be hard to pull the jacket off at that long. This stuff's pretty slippery. So you can see that went fine. And I didn't even nick the foil, so that went well. So I'm removing the foil. Off that end, and then I'll do the same thing off this other end. And again, I'm going to want at least that much off. Okay, so I've got my two ends stripped. Again, just reiterating, this is not a typical application where you only have 4 or 5 inches of jacketed shielded cable left. And just also to reiterate, I would only land one of these, the shield wire, I would only land it on one end or the other. So I'm just going to cut off this end that's up at the PLC. And for this example, I'm going to use pair 1. So you can see I've got, this is pair 2 down here. So I'm going to be using pair 1. So I'll just strip the end conductors there. Again, being careful to not get any copper pieces down by the PLC. Okay. And these wires are nice and already twisted. So then I'll use my little screwdriver to land the black wire on terminal 6. And you can see I stripped a little bit much there, so I'll cut off a little off the end. And in twisted pair cabling, you typically want to keep them twisted as much as possible right up until the point at which they land. So I will try to thread into both 4 and 6. Okay, and I will thread those through there, and now I'm going to, this jacket is making it difficult to lay out nice, so I'm actually going to strip a little bit more off of this. So you can either strip more off like I am, or you guys actually have a little bit more of this cable than I had left on this sample here. It might make the most sense for you to just kind of run it down and back to double it over itself to make more room, as opposed to what I'm doing here. Okay, so let's try that again. So I'm just going to kind of wrap pair 2 down in there for now. And like I said, if we get to it, we will land that later on the analog output. And so do the same thing with this pair 2. I'll tuck those down in. And then this is the pair 1 that I'm working with. So I will strip the ends of those. Going to land the black one on this terminal block here. Tug on it, tug on the other ones that were under it to make sure I didn't loosen them up. That all looks fine. And then I will land the white one on the wire coming from the analog potentiometer. And you'll have a wiring diagram showing you which terminals go where. Okay, kind of neaten those up there as they stick down in. And I'll feed these ones back under that just to help hold them down. Okay, and then this last one, the shield wire, just for demonstration purposes, I'm going to land it on this gray wire as if this gray wire was a ground block. You know, actually I'm going to swap out that gray one for a green one just to make that clear that I'm pretending this is the ground reference point for our panel, because we typically use green to represent ground. And you can just land it on your gray block that was there, but I'm trying to highlight for you that we're pretending that is our single point ground for the field devices. Okay, so we've now run a twisted pair from the positive voltage coming from the potentiometer, the negative is from our zero reference, and then they go into common and the voltage input 1. It's a shielded cable. We carefully stripped it to protect the shield, and we have our shield wire landed on our simulated ground for the panel. So that's it for connecting it. Now let's go take a look in the PLC and see if it's functioning as we'd expect. Okay, so we have connected components workbench. Just as a reminder, we've already configured our IF2. Looking down here in the first slot, we have a single module, and we've configured it to be voltage. We're connected to input 1, so really I can disable input 0 if I want, since I'm not using it. And I'm going to set the frequency, how often it is reading that voltage. I'm going to set it to 250 Hertz. So I'll go ahead and download that to get those settings updated, disabling input 0 and changing the frequency on input 1. Okay, so that's downloaded, we're connected. I don't have any program running in the PLC. This one was just a blank one from us setting it up. But if I go and look at global variables, again, here's all of my standard inputs and outputs, the digital ones. If I scroll down to the bottom, you can see input 0 and input 1. So input 1 is the one that we are wired to. And you can see it's kind of bouncing around a little bit. And that comes back to that idea that I was telling you about, where the resolution is only 12-bit, but the number is 16-bit. So there's basically some noise in the variable itself. So that's with the potentiometer turned all the way to the right. I'm going to start adjusting it to the left now. And you can see the numbers increasing as I rotate it. So we went from 0 to, if I go all the way to the left, let's see what we get up to. So we get up to about 60,850-ish, we could say. 60,850. So let's divide 60,850 by 65,535. So that's about 0.928, and if we multiply that times our 10 volt range, That's about 9.285 volts, roughly, is what, if everything was perfectly calibrated there as far as our bits to the voltage divider. And we said we were expecting a little under 10 volts. I think when we actually measured it, the range was 0 to 9.4. So that's a really quick example of how we would scale that number. And so we will go into the scalar instruction that lets us take that 0 to 60,000 range and turn it into units that mean something for our process or whatever program we're doing. Okay, so we now have completed the installation of the module, the wiring from the module to the potentiometer, and we've covered what type of data is being created in the PLC. A number varying from 0 to around 60,000 in this case. Okay, that's it for this lesson. Well, thanks.